Hello and welcome to another lecture for ECE 108 and our final lecture for introducing new combinatorics arguments. So in this lecture we're going to talk about the principle of inclusion-exclusion, and then we're going to talk about the idea of complementary counting. So we've already given one example of using inclusion-exclusion in the previous lecture where I discussed the number of ways that you can roll 3d6 and end up with a sum of 12, but we're now going to formally introduce this idea. Okay, so in a town with 351 adults, every adult owns a car, motorcycle, or both. If 331 adults own cars and 45 adults own motorcycles, how many of the car owners also own a motorcycle? So in order to tackle this problem, we're going to do a different technique than the methods that we've used before. So here we're going to let M and C be the sets of adults that own a motorcycle and a car respectively. So to be explicit, M is the collection of adults that own a motorcycle and C is the collection of adults that own a car. So the problem statement tells us some information. One, every adult owns a car, a motorcycle, or both. So what does that tell us? Well, if I take the adults in M and I union that with the adults in C, that is the collection of all adults who own a car or a motorcycle or both. So that tells me that the cardinality of M union C is simply 351. Further, I know that 331 adults own cars, so the cardinality of C is 331, and 45 adults own motorcycles, so the cardinality of M is simply 45. So now, in the question, we want to know how many of the car owners also own a motorcycle. Well, within our set notation, that would simply be M intersects C, the cardinality of that set. So given that the cardinality of the union is this and the cardinality of the individual sets is that, is it possible to find the cardinality of M intersect C? Well, in other words, is there a relationship between these four sets? Well, yes, there is a relationship between the cardinalities of these sets. So let's look at a picture. So here I have my set M, I have my set C, and here's my intersection between the two, and if I combine them, I get the union. So let's use a hand-wavy counting argument to try to find a relation between the cardinalities of these sets. So if the intersection is empty, then the cardinality of M plus the cardinality of C is simply going to be the cardinality of the union. Why? Well, any element of M union C is either an M or C, and if the intersection of M and C is empty, then this equality here holds exactly. So now, on the other hand, if M intersects C is empty, then the cardinality of M plus the cardinality of C is bigger than the cardinality of M union C since I've double counted something. So to be explicit, if I have George sitting over here, that's in both of these sets. If I count the things that are in M, I count George. And then if I count the things that are in C, I also count George. So in this case, the cardinality of M plus the cardinality of C counts George twice. So in slide form, the elements in the intersection are double counted. So now if I want to turn this inequality into an equality, I need to subtract things off from this side here. What do I need to subtract? Well, I need to subtract exactly the double counted elements. So what are the double counted elements? Well, that's the things that are in this intersection. So I get this exact equality here. And notice that this equality here holds in this previous case as well, since this is just simply 0, and if I subtract 0 from this side, it doesn't change it. So this expression here is how the cardinalities of these four sets are related to each other. So thus, if I apply this to the previous example, I have this thing here is simply going to be equal to this expression here, just plugging in the values of MC in the union, which is simply 306 adults. Okay, so now let's give a definition. Principle of inclusion/exclusion. For all sets A, B, and C, the cardinality of this is equal to the cardinality here. Basically that argument that I outlined on the previous slide. And if I have three sets, this is what the expression becomes. So for three sets, what do I have to do? Well, let's draw this out real quick. So if this is A, this is B, and this is C, if I take A, the cardinality of A plus the cardinality of B plus the cardinality of C, I have double counted all of the things in these intersections. So now what I can do is I can remove these intersections by, say, taking my A union B, this cardinality, say, here, and subtracting it. And then I can take my A union C, the cardinality here, and subtract it. And then I can take this cardinality of the intersection between these two sets here and subtract it. So subtract that off. I apologize, I'm running out of colors here. There we go. So if I subtract off all of those, well, originally when I added these together, I triple counted the thing in the middle. But now by subtracting off these intersections, I've subtracted off the region here 3 times. So I added it 3 times, then I subtracted it 3 times. So I still need to include the things that are in the intersection. So that's why I have this last element here. So this is the basic idea for how you argue that this equality holds, and you can build higher dimensional analogs for arbitrarily many sets. You just keep adding and subtracting things as you go along. So yeah, it gets a bit messy with more than 3 sets, but you can do that, and at most for this course I'll ask you to do it for 3 sets. Okay, so yeah, again, this can be generalized to an arbitrary number of sets. So this is what I will refer to as the inclusion-exclusion principle. Okay, so let's look at some examples. How many integers from 1 to 100 are multiples of 2 or 3? So here I'm going to let A be the set of all the multiples of 2, and I'm going to let B be the set of all the multiples of 3. So here I want to find the multiples of 2 or 3, so I want to know what the cardinality of A union B is. So from here, to do that, I need to first know what the cardinality of A is, what the cardinality of B is, and what the cardinality of the intersection is. So clearly, the cardinality of A is 50. So to find this, you could use a counting argument by noting, hey, exactly half of these are going to be divisible by 5, or you could physically count them. I don't recommend counting them physically, though. And the cardinality of B is simply going to be 33. So now, we want to know how many elements are in A intersect B. Well, the elements of A intersect B are going to be exactly the elements that are divisible by 2 and 3. So now note that the numbers that are divisible by 2 and 3 are going to be exactly the multiples of 2 times 3, which is just 6. So now all we need to do is calculate the number of multiples of 6 between 1 and 100. So the number of multiples of 6 between 1 and 100 are, well, I'm going to use this shortcut here. If I take 100 and divide it by 6, that will give me a number with potentially some things following a decimal. And if I take the floor of it, so this symbol here is the floor, that just tells me what the integer part of that is. So 100 divided by 6 is 16 point something. Therefore, there's going to be 16 numbers that are divisible by 6. So again, you could use a counting argument here, but I'm just going to use this to make it a bit quicker. Okay, so from here, the number of numbers that are divisible by 2 or 3 will simply be the cardinality of A union B, which is simply going to be cardinality of A plus cardinality of B minus A intersect B. And we've computed these numbers, so that's simply this thing here, which is 67. So the vast majority of the numbers in this case. Okay, let's look at another example. Your overly nice instructor, not me, decided to give the poster of every 11th post on Piazza 1 point of extra credit on the midterm, and every 13th post on Piazza 1 point of extra credit on the final. In addition to these first 2 rules, the instructor added another rule. Posts that are both an 11th post and a 13th post only get the extra credit for the final. So now I can ask a question. If there were 1,000 posts on Piazza over the term, how many points of extra credit were given out? So to compute this, I first need to find how many 11th posts there were. I then need to find how many 13th posts there were. If I add those together, that tells me the number of points given on the midterm and the final together. But I double counted the points where it was both an 11th post and a 13th post by giving them credit for both the midterm and the final. So I then have to subtract off those extra points. So to be explicit, this is the number of points that were given on the midterm. So again, take 1,000, divide it by 11, take the integer part of that. The number of points given out for the final would then be 1,000 divided by 13, the floor of that, which would simply be 76 points. And the number of points where I double counted would be exactly the multiples of 12 and 13. So that would be 1,000 divided by 11 times 13, or 6 points that were double counted. So thus, by the principle of inclusion-exclusion, I have to subtract these out from my sum of the points from the midterm and the final. And thus, I get 90 plus 76 minus 6, or 160 points given out in total. So yeah, this principle here is probably one of the most powerful techniques that we have for counting. You can take a really hard problem, split it into an easy problem that overcounts things, and then you can compute the number of things that you overcounted, which ideally will be an easy problem, and subtract that from your first number. And for very difficult problems, you can repeat this process multiple times. An example of that would be this expression that I had over here. Right? I start by adding things, I subtract things, then I add things back. You can keep doing this process to continually take a hard problem with big numbers and whittle it down to smaller and smaller problems. Okay, so now let's introduce another counting technique, complementary counting. So for sets A and B with B as a subset of A, this is a true statement. A good exercise would be to prove it. It's not too difficult to prove, but I digress from there. This can be used in counting. So in counting, there are many problems such that the original problem, say B, is not very nice to count, but its complement, B complement, would be easy to count. So in those cases, I can use this equality here to be able to count the number of elements with property, to be able to count the number of elements of B by simply finding the number of elements of B complement and doing the subtraction here. So let's give a concrete example of this. How many positive integers less than 100 are not multiples of 5? So we could do this directly, but we'd have to do a lot of cases. For instance, we could say it's a multiple of 2, but not of 5. It's a multiple of 3, but not of 5, etc. That's tedious. It's unnecessarily tedious. So here, to avoid doing all of these cases, I want to apply this principle here. So how can I do that? Well, first I need to know what A should be for this problem. In general, when applying the complementary counting principle, you need to let A be the set of all of the possible events for this problem in consideration. So here, A will simply be the set of all positive integers less than 100. Now B is going to be the collection of all positive integers less than 100 that are not multiples of 5. So B is the thing that I want to compute, but it's kind of hard to compute on its own. So from here, clearly, the size of A is simply going to be 99, and the set B bar is simply going to be the set of all integers divisible by 5. So notice here, I changed the not a multiple of 5 to divisible by 5 or not a multiple of 5. Those two statements are equivalent. Now, I know how to compute the size of B complement, right? Size of B complement is simply going to be this value here, or 19. So now I can put these together and use my complementary counting technique to know that the cardinality of B is the cardinality of A, 99, minus the cardinality of B complement, 19, which is just simply equal to 80. So from here, there's 80 positive integers less than 100 that are not a multiple of 5. So this argument here is a lot easier than actually going through and computing all of these positive integers less than 100 that are not multiples of 5, simply because I know how to compute the multiples of 5 rather quickly, but I don't have a nice argument for how to do this. Okay, in general, you might want to consider doing complementary counting whenever you have a problem that is kind of obnoxious with what it's asking you to compute. Another time when you might want to use complementary counting is when you know that the size of B is going to be much bigger than the size of B complement, and the size of B complement would be relatively easy to compute. Okay, let's look at a few more examples to end the lecture with. How many positive integers satisfy this equation here? So you might think a priori that this is similar to the problem that we considered before, but it's not. So if I were to try to do the stars and bars type method, here in my bins, this bin on that side, whenever I put, quote, one ball into it, it changes the number of balls that are in the bin based off the values of balls that are in the bin. So this thing here is non-linear, so the standard method doesn't work. So namely, if I try to put one thing in, I end up with only one, but if I go to put two things in, I end up with x to the fourth things sitting there. So our previous method does not really work. So here, this is a good example where case analysis is nice. So what am I going to do case analysis on? Well, I have two options. I have x and I have y. So before we blindly jump in and start doing case analysis on one of them, let's kind of think through it a little bit. If I do case analysis on y, well, I need to check all the possible values of y from 0 all the way up to 69. Whereas if I did case analysis on x, whenever I plug in a number in for x, I take it to the fourth power, so that dramatically decreases the number of cases I need to consider. So let's do case analysis on x. So in general, when doing case analysis, you should carefully consider what you want to do cases on. Okay, so for x is equal to 1, this equation simplifies to y is less than 69, and in this case, there are 68 solutions. Now, if x is equal to 2, I get a 2 to the fourth, subtract that off, and that equation becomes x is less than 54, and in this case, I know there's 53 solutions. And next, if x is equal to 3, this simplifies to y is less than negative 11. There are no positive solutions for that case, and thus there's going to be no positive solutions for any x greater than or equal to 3. Thus, there's 68 plus 53 is equal to 121 positive integer solutions to this equation here. So do keep in mind, if I give you random questions like this, sometimes you do have to go back to your roots of manually counting and doing case analysis. The fancy techniques that we've introduced over the last 3 lectures or so are not always applicable. Let's look at another example. How many ways can you make 68 cents with quarters, dimes, and pennies? So here I'm assuming I have an infinite number of quarters, an infinite number of dimes, and an infinite number of pennies. So we can convert this question here into an equation. So in particular, we want to know the number of solutions to this equation here, where x1, x2, and x3 are non-negative integers, and x1 represents the number of quarters, x2 represents the number of dimes, and x3 represents the number of pennies. Now, again, you might think, hey, this is a linear equation this time. If I plug in one ball versus plugging in 2 balls into any of these slots, it has the same relative effect. Maybe I can go back and modify the result that I had from the previous lecture to apply to this problem. And there are some things you can do along those lines, but generally speaking, to solve this solution, it's easier to use case analysis. So what should I do cases on? I could do cases on x1, x2, or x3. Well, if I do it on x3, I'm going to have to consider a lot more cases because x3 doesn't have a multiplier on it. If I used x2, that's better than x3, but still it's not the best, right? I'd have to consider 6 different cases for that to work. But on the other hand, if I do x1, there I'd only have to consider 2 cases because x1 clearly can't be 3 because 3 times 25 is 75, which is bigger than 68. So we consider cases. x1 can't be larger than 3, so I'm doing cases on it. So here here I consider the case where x1 is equal to 2. In this case, I have this equation here, and I need to know how many solutions there are here. Here, clearly, x2 can take on the value of 0, and it can take on the value of 1, but it cannot take on the value of 3. Thus, there's going to be 2 solutions. Next, if x1 is equal to 1, the equation that I need to consider, this equation simplifies to this thing here. So explicitly subtract 25 from both sides. Here, there's going to be 5 solutions. x2 is equal to 0, 1, 2, 3, or 4. So we get 5 solutions in this case. Last, if x1 is equal to 0, and then this case, I have this quantity here, and here there's going to be 7 solutions. x2 could be 0, 1, 2, 3, 4, 5, or 6. So clearly there's 7 solutions. So in total, I can add these up to get 14 ways of solving it. Okay, so again, we can't always use fancy methods. Sometimes you can, sometimes you can't. And for this case, overcounting might be a useful method to apply. So now let's look at one final example. Dr. Nim is a 2-player game where there's 8 objects, and each turn a player removes between 1 and 4 objects. How many different games of Mr. Nim are there? So in the classic version of Mr. Nim, there's 12 objects, but I lowered it down to 8 for this question. So how can I find the total number of different games of Mr. Nim? Well, let's first reformat this question into a format that we've seen before. Games of Dr. Nim are going to be solutions to this equation here, where all of the xi come from the set 1, 2, 3, and 4, and order matters. So x1 is different than x2, so these things here are different bins. So these terms here are all distinct. So there's kind of a problem sitting here, right? I do not know what each of these xi terms are, and I do not know what n is. So ultimately, I need to do some case analysis somewhere to solve this problem. So I could do case analysis on n. You can note the minimum that people can take is 1. So the largest value for n would be 8. And then I could ask, what are the solutions to this thing here for values of n ranging between 1 and 8, and add up all of those cases. So that's something I could do. And the math there is a little bit more involved because I always have to worry about going over this limit of being between 1 and 4. And no matter what transform I do, I'm going to have that issue for some of those equations at a minimum. So instead of doing that, I'm going to do case analysis on the number of times xi is equal to 1 is played. So here I can formally use the pigeonhole principle to note that the largest number of times xi can be played is 8, because if it's played 9 times, then I break this going over 8. So now in what follows, I'm going to introduce a notation just for this problem. I'm going to use the notation, these ordered pairs n1, m1, n2, m2, etc., to denote the game where these combinations were played. So to be explicit here, the game where the first player picks a number 4 and then the second player picks a number 4, that would simply be denoted by 2, 4, because in the game, 2 number 4s were picked. To give another example, in the game where one player plays a 2, the other player plays a 2, and then the final player plays a 4, that game would be denoted by, 2, 2, 4 are the orders in which the things were brought up. That game would be denoted by 2, 2, because there's 2 number 2s, and 1, 4, because there's 1 number 4. So I'm simply using this notation here out of convenience. Okay, so for the first case, if I played 1 8 times, the only game in this case would be 8 number 1s get played. And there is only one way to arrange this because both players just take 1 each time. Okay, now for games where 7 number 1s are picked, there are no actual games because the last player only has the option to take 1. So next up, 6. If number 1 is played 6 times, the only possible game left over is that the final play, or the final remaining play, has to be a 2. So the only games are the games where 6 1s are played and 1 2 is played. So how many games can be played where 6 number 1s pop up and then 1 number 2 pops up? Well, here there's 7 bins to play with, like this, and I get to choose one place to put a 1 in there. So this is a simple combinatorics problem. It's 7, choose 1, or simply 7, because there's 7 places where I can pick where the 2 goes. Okay, so what about games with 5? Well, if I play 5 ones left, then the remaining terms have to add up to 3, and I can't pick a 1, so the only way I can do that is by having 5 ones played and then 1 3 being played. So in this case, I have a similar type of combinatorics argument. There's 5 plus 1, 6 turns in the game, and I have to pick one of the terms to put the 3 at. So from there, I get 6 options to stick the 3 in. Therefore, there are 6 games where 1 is played 5 times. What about the games where 1 is played 4 times? Well, now I have options. So if I play 1 4 times, there's 4 points remaining. And out of those 4 points, someone could either play a 4, or someone could play 2, and then we could play another 2. We can't pick 3 because then someone would have to pick a 1. So we have this option here or this option here. So out of these 2 options, how many ways can I rearrange the turns in the game? Well, here I have 4 plus 5 turns, and I need to pick one spot for, say, the 4 to go. So from there, there's going to be 5 options. And for the second one, I have 4 plus 2 turns, so 6 turns. And I need to pick 2 places for the 2 to go. So that'd be 6, choose 2. Okay, next up, let's look at 3. So if 3 ones are played, how many points are remaining? Well, 5. So how many ways can 5 be written as a sum of 2, 3, and 4? Well, only one way, right? I need to have the 3 ones being picked up, and then I need a 3 and a 2. There's no other ways I can get to the 5. Thus, from here, I need to know how many ways I can rearrange this. Well, there's 5 turns that are being played, and I need to pick somewhere to put the 2 and then somewhere to pick a 3. So their order matters with where I put the 2 and where I put the 3. Therefore, there will be 5 times 4 games in the case where I have 3 ones. So now let's look at the case where I have 2 ones. So if there's 2 ones, I have quite a few more options. So here, just for reference, let's note that the numbers have to be 1, 2, 3, or 4. Okay, so if I picked 2 ones, how many points do I have remaining? Well, there's going to be 6 points remaining, so I could pick 3 twice, or I could turn around and I could pick 4 and then a 2 in some order. Or I could turn around and I could pick 3 2s. So these are the total possible games that can occur. And again, I need to know the order here. So here, how many games can take place that look like this? Well, there's 5 slots in total, and I need to say pick 3 of them to put a 2 in. So from here, that'd be 5, choose 3. In this case, there's 4 slots in total, and I need to pick somewhere to put a 2 and somewhere to pick a 4. And how many ways can I do that? Well, 4 for the 2 and then 3 for the 4. So it's going to be 4 times 3. And then for the last one, there's 2 plus 2 or 4 turns. And I need to pick a slot to pick the 3s or the 1s equivalently. So in that case, I'd have 4 choose 2 games. Okay, next up, if I only picked 1 1, there's 7 points remaining. So let's just break down the cases there. So I could pick 2 2s and 1 3, or I could pick 1 3 and 1 4. So those are the only options here. And then I've done quite a few of these combinatorics arguments. So that would simply be 4 times 3 for this, and 3 factorial for here because I'm just rearranging the orders in that case. And finally for 0 ones, I have 8 points to divvy up between 2, 3, and 4. So I could do 2 4s, or I could do 1 4 and 2 2s, or I could do 4 2s, or I could do 2 3s and 1 2. So again, just breaking down the number of possibilities by brute force here. Thus, there would be 1 plus 3 plus 1 plus 3 games in this case. So yeah, now if we add up all of these possible games together, we can note that there's exactly 108 different games in this case. So again, case analysis is a thing. you're not going to necessarily get away from case analysis, but when you have to do it, think carefully about the cases that you pick. Okay, so that aside, for your assigned reading, I want you to read pages 77 through 78, the inclusion-exclusion stuff. There's literally less than 2 minutes of reading there, so just do the reading there. And we have a meme. Counting, upgrade, all of these different counting methods. Go back, go back. Okay, so I will talk to you in the next lecture and have a wonderful day.